something with circuits. I've already completed that GE requirement that knocks out both sections. Is that can I still take my second GE in
just to be full time?
just full time over the summer?
It depends. So every agency kind of has different definitions for like what constitutes full time. Because
like 3 units for
yeah, but then some place of restriction where like that has to be counted towards your degree requirements, and so
right.
So I would check with the VA office and see kind of what they determine as that.
Yeah, maybe that question.
Yeah.
Oh. If solid mechanics lab is built on the summer here.
Typically, no. The only summer courses we typically offer are is 2 senior labs. So that's 476A, 476B, and thermodynamics 304. I know there's been talk that we want to offer more summer courses this summer, but I honestly don't know how successful it's going to be because the school is very strict in terms of like you have to have X amount of students in your summer course. Because if it's under enrolled, then the school just cancel it.
On what basis?
Because they have to provide funding for it. So they said if it's not serving enough students, then for the school they think it's not worth it to offer that course. So yeah. So I think we're going to try to offer more summer courses, but if it's not enough enrollment, then the school will cancel it.
I just have a question.
Sure.
So for part A on this question, I ended up getting a negative 4.05 for A, but on the solution sheet, you had it as a negative still with the negatives not cancel out for like for when you plug it in.
So that negative is there because remember, when you're working with physical systems, you're never going to get a situation where you have a positive exponential. So that negative is just there, just saying that, this is a physical
Mhm.
problem. You should have a decaying exponential.
Okay.
So you should have a negative.
No, I
Yeah.
used the negative all throughout the problem,
Good, good.
but so it would always be negative.
It would always be negative.
Okay,
Yeah.
cool. Okay, thank you so much.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today?
Good.
Good to hear. Awesome. All right, so we're end of week 4. So yeah, I know things will probably start to get really busy. So we're not quite midterm yet, but I know it's probably on everyone's mind. So remember, Laplace transforms, this is going to be our last topic before the midterm exam. And so I think, so after this, then, we'll kind of move on to other stuff. But yeah, I expect you guys to, start getting busy, homework's going to start piling up and, you're going to start to have exams. So yeah, now is the time to kind of lock in for the semester. Okay, so yeah, our plan, we're just going to keep going with our set of lecture notes on Laplace transform. So we kind of introduced the idea last time. Today, we're actually going to start to actually use it for its intended purpose, which was, to solve differential equations. We may not get all the way through an example problem with that today, but I do at least want to introduce the concept of it, just so that we can start next Tuesday, kind of in the ground running. Okay. All right. Any questions I can answer before we get started for today? Okay. All right, so let's go ahead and pick up where we left off. Okay, so last time we actually left off on a pretty nice spot, and so we were basically just finished up an example. Okay, so last time we did a lot of practice in terms of taking Laplace transforms. We introduced this idea of the Laplace transform table, and we did a lot of practice in terms of finding inverse transforms. Okay, so today will be kind of the first wrinkle that we kind of throw into the whole process, which is this idea of shifting. Okay. So there are 2 shifting theorems in Laplace, and they're named very appropriately. So there's the first shifting theorem and the second shifting theorem. So we'll go over the first shifting theorem today. Okay. So the first shifting theorem is often called the S-shift theorem. And so the idea with the S-shift theorem is that, if you have some function, f of t, okay? Right. And let's assume that we know that it's Laplace transform. So let's say that the Laplace transform of f of t is big F of s, okay? So we'll assume that this is known. Right. So f of t could be just a function that we have in our Laplace transform table, right? So we know what its Laplace transform would look like, right? So the first shifting theorem states that, if you take f of t and you multiply it by an exponential function, so let's say you multiply by e to the at, okay? Right? So you just take the product of an exponential function and f of t. Remember, f of t is the previous function that we know the Laplace transform for, okay? If you take the Laplace transform of both of these functions combined, right, then what the first shifting theorem basically says is that this is going to be the Laplace transform of f, so the same Laplace transform, except that you're going to replace s with s minus a. Okay. So in other words, what we see here is that, our Laplace transform has been shifted by an amount a, where that a was the exponent in the exponential term. Okay. Okay. So just a very quick example of this theorem in action, right? So let's say that we have f of t is equal to t squared, okay? So according to our table, we know the Laplace transform of this. So we know the Laplace transform of t squared is 2 over s cubed, okay? Right. And so if we multiply t squared by an exponential function, so let's say we take, e to the 4t times t squared, okay? And we take the Laplace transform of it. Okay. And so what the first shifting theorem basically says is that, you would then take just the Laplace transform of t squared, and then you replace s with s minus 4 in this case, okay? And so what this e to the 4t does is that it essentially shifts your Laplace transform by 4 in the Laplace domain. Okay. And so the Laplace transform of this is going to be 2 over s minus 4 cubed. Okay. Okay. All right, so the proof of this is actually very easy. I usually don't do too many proofs in this class, but I think this one is worth looking at. Okay. All right. And so let's prove. Okay. So let's prove the fact that if we take the inverse Laplace transform of f of s minus a, okay, this is going to give us e to the at times f of t. Okay. Okay, so to prove this, we're going to write out the integral expression for big F of s minus a. Okay. Right. So according to our definition, or our integral definition of the Laplace transform, if we go ahead and plug in s minus a, this is integral from 0 to infinity of e to the minus s minus a multiplied by t times f of t dt. Okay. Right. So all I did was, take the Laplace transform of f of t and then just replace it by s minus a. That's essentially what we're doing with this expression here. Okay. Okay, so let's rearrange these terms. So because we have our exponential term in our in our integrand here, we can go ahead and swap out or pull out the e to the at. Okay. So this is integral from 0 to infinity, e to the minus st multiplied by e to the at times f of t dt. Okay. And then from here, it's very clear, right? If we kind of take this as like just a package deal, right? And so if we take everything in that square brackets as a package deal, you can see that everything else there is just the standard components of our regular Laplace transform. And so this tells us that this is the Laplace transform of, or this entire expression of e to the at f of t. Okay. So thus, if you have e to the at multiplied by f of t, you just plug it straight into the Laplace transform you get. Big F of s minus a. Okay. All right. So very straightforward. And so, basically when you multiply by an exponential in the time domain, that results in a shift in the Laplace domain. Okay. So there's a lot of applications for this because, if you think back to our solutions to second order ordinary differential equations, we had a lot of situations where we had an exponential term. And so the fact that, multiplying by an exponential in the time domain just ends up being an algebraic shift in the Laplace domain is actually very, very helpful. Okay. Okay, so let's do an example to kind of show why this is helpful. Okay. Okay, so let's say that we have the following Laplace expression. So let's say we have f of s is equal to 3s minus 137 divided by s squared plus 2s plus 401. Okay, and then what we want to do is we want to find the inverse Laplace transform of this expression. So this is something new, right? So this is actually quite different from all the examples we did on Tuesday, right? And so on the bottom, we actually have a quadratic expression. So it's not just an individual term, okay? So we're going to do something with that quadratic equation down there that, you probably haven't seen for a while. And honestly, probably the first time you learned this, you thought there was no way that this has any practical application other than just being a neat party trick. But we are going to go down there. We're actually going to complete the square. Okay. And you'll see why in a second. But okay. So let's go ahead and complete the square. So we have s squared plus 2s, right? So that's kind of our stem, right? So that's our start. That's the start of our square. And we want to basically add something, okay, so that we can get this into an expression s plus something else quantity squared. Okay. Okay. All right. And so, if you think about it, right? So let's say that, let's look at the quantity s plus, we'll just give a generic variable here. So let's do s plus k, right? Quantity squared. And so if we actually FOIL that out, we get s squared plus 2ks plus k squared, right? That means if we want to complete the square, right, we need to look at the second expression in our quadratic, right? Essentially, we need to solve for what k is based on this expression. Okay. Okay. And so looking at this quadratic equation here, we have s squared plus 2s, right? So this tells us that 2, if we want to complete the square, has to equal to 2k, right? Which for this situation is very straightforward. This tells us that k must equal to 1, okay? That means if we want to complete the square, all we have to do to this is add 1 to this equation. Okay, so if we do that, we have s squared plus 2s plus 1, right? And so if we're going to add plus 1 here, we have to subtract 1 on the outside. Okay. Right, and then we still have that 401 that's kind of hanging out there. Okay. All right, so now what this allows us to do is in that now lets us complete that square. So now we have s plus 1 quantity squared plus 400. Okay. Any questions on how we completed the square on the denominator there? Okay, good. All right, so why are we doing this, right? So if you look at this, right, and so let's ignore, right? Let's ignore that the 1 is there for a second, right? And so without the 1, okay, right? So that plus 1 still exists, and so we're not going to forget about it. But for now, we're just going to look at this as s squared plus 400, right? And so if we kind of look at this a bit more carefully, we can see this is equal to s squared plus 20 squared, right? And this is in the denominator of our Laplace expression. So why is that significant? Well, if we go back to our Laplace table, I'll come back, don't worry. Right? We look at our Laplace table, right? And we see that whenever we have s squared plus something else squared, that looks a lot like our sinusoids, right? Because both cosine omega t and sine omega t, if we take this Laplace transform, we end up with s squared plus omega squared in the denominator, okay? But we don't have s squared plus omega squared. We have s plus 1 quantity squared. Okay? Look what else we have here in our table. Okay? Right? We have the Laplace transform of e to the at times cosine omega t, e to the at times sine omega t. Right? Look and see how these denominators are formulated. Right? So they are in the form s minus a quantity squared plus omega squared. Okay. So this looks a lot like what we just found. And if we think about it in terms of what we just learned at the beginning of lecture today, in terms of first shifting, right? So these expressions that we have in the table for e to the at cosine omega t, right? And these two are nothing more than just shifted versions of these ones. Okay. So the reason we have them in the table is that, e to the at cosine omega t, e to the at sine omega t, these are fairly common that you'll see in our application. So, they get their own entry. But, technically speaking, we don't need these entries in the table because we can find them based on cosine omega t, sine omega t, and then applying our first shifting. Okay. Okay, so let's go back. Right. And so the fact that our function now is f of s is equal to 3s minus 137 all over quantity s plus 1 squared plus 400. Okay. Right. Just based on the structure of the denominator, we can say that this is going to look like a decaying exponential, okay, or decaying sinusoid. Okay. So essentially just shifted versions of cosine omega t, sine omega t. Okay. Okay, so let's kind of move forward with that kind of understanding that we're looking for these types of situations. Okay. All right, so actually let me do this too. So just to make things clear, I'm going to replace the 400 with 20 squared. Okay. All right, so right away we can kind of start to fill things in, right? So based on the shift here, and based on kind of what we know here, we can say that our shift amount A is going to be -1, right? And we can tell from our second term here that our omega is going to be equal to 20. Okay. Okay, so let's go ahead and move forward with that. So, in order to get the Laplace transform of e to the at cosine omega t, we need to get the same shift up in the denominator, right? Because e to the at cosine omega t, the Laplace transform of this is s minus a all over quantity s minus a squared plus omega squared. Okay. Right, so we have the denominator exactly where we want it. The only thing is that we have to manipulate the numerator in order to match the denominator. Okay. In other words, we need to get s minus a up in the numerator in order to make this inverse possible. Okay. All right, so once again, we're gonna have to do some algebraic kind of tricks here. So we're gonna basically just add 0 to our equation. Okay. So let's do this. me actually leave some space here. Okay. So let's do this. So we know that we need to get s plus 1 up in the numerator somehow, right? But s is not by itself in the numerator. You can see we have 3s. And so in order to get s plus 1 in the numerator, let me go ahead and add 3 to this, okay? Let me use a different color to kind of show what I'm doing. Okay, let me use red here. Okay, so let's add 3 to the numerator, okay? That way we can basically take this expression here and factor out a 3, and that'll give us s plus 1, okay? But since we're adding 3, we also have to subtract 3 as well, okay? Because we can't alter the value of the expression, but we can kind of add, numbers in the middle in order to kind of make it work, okay? And so by doing that, what we get is we get 3 times s plus 1 minus 3 minus 130, so that's a minus 140, all over s plus 1 quantity squared plus 20 squared, okay? All right, so all I did in that step was that, we know that we need the s plus 1 in the numerator in order to match our expression together with e to the at cosine omega t, okay? And so I basically just added 3 to the left part of the expression to be able to factor out 3s plus 1, and I subtracted 3 in order to keep the value equivalent, okay? All right. So I know that I did that step kind of fast, but there's this step here is pretty crucial, and that's part of kind of the algebraic tricks that you have to do in this section. Okay. Let me go ahead and separate this out. So now that we have 2 terms in the numerator, we can go ahead and separate them out. So we have 3 times s plus 1 all over s plus 1 quantity squared plus 20 squared minus 140 all over s plus 1 quantity squared plus 20 squared. Okay. Okay. So now that we're here, we can see that the left term there, if you ignore the 3, this is equal to the Laplace transform of e to the minus 1 times t times cosine of 20t. Okay. Right. So the cosine term is good to go. For the other term here, we do have to kind of work on it a little bit. And so we know that the other term is going to involve sine omega t because there's no s term in the numerator there, okay? And so if we go back to our table, we can see that if we look at the Laplace transform e to the at sine omega t, okay, this is omega divided by s plus a, or s minus a, excuse me, s minus a quantity squared plus omega squared, okay? Right. So we know that second term is probably going to be an e to the at sine omega t, just based on kind of what we've seen so far, right? The only thing we have to do is we just have to manipulate the numerator so that we get omega up there, okay? So we're in luck. Okay, so we have 140 up here. So we need to manipulate this so that we get 20 up here. So luckily for us, that is pretty straightforward. So we just have to factor out 7, right? And so we have minus 7 multiplied by 20 over s plus 1 quantity squared plus 20 squared. Okay. So then now this here is the Laplace transform of e to the minus t sine of 20t. All right. All right, so now that we've done all the hard work, we are ready to do the inverse. And so, our inverse here, we just have to plug in these expressions here, and then we just have to take our constants along to the right. So f of t for this problem is equal to 3 e to the minus t cosine of 20t minus 7 e to the minus t sine of 20t. Okay. And if you compare this solution here to, our second order ordinary differential equations, you can see that we have our characteristic damped oscillator. So the sine and cosine of 20t means that our solution is going to oscillate up and down, okay, just like a sinusoid does. And then the e to the minus t there will ensure that our, the amplitude of our oscillations does decay with time. Okay, so this is a characteristic, solution that we would get from, let's say, a mass spring system which oscillates, but has some damping, so it decreases. Okay. Okay. Any questions on this example here? Okay. All right. So, so I know for these problems, it's going to seem like I just pull these just seemingly magic tricks of algebra from my hat. And so, it is, I think when you first see it, it is like, how did you know how did you know to complete the square? So, a lot of this is kind of just, pattern recognition. You see kind of a lot of these things. You kind of see like, oh, that's kind of where I should go. That's what I should do. So, yeah. So with these ones, the best thing to do is just to kind of look at a bunch of examples. I'm going to try to do a lot of as many examples as I can in class. Then you'll start to kind of recognize, say, that's where I should kind of go with this. Okay. The other benefit you'll have is that, eventually we'll be solving differential equations. And so, by this point, you should know kind of what our differential equation solution should look like. And that'll kind of tell you where to go as well. Yeah.
Oh, I was just about to ask, today, are we going to go into the total going from little ft to big fs and then going all the way back to what we got right here with the damped oscillation equation?
Yeah. So my plan is to get to, solving differential equations. So that's going through your differential equation. You take the Laplace transform, you solve for the solution in the Laplace domain, and then you would then invert that to go back to the physical domain. So that is actually the next thing that we're going to do. Okay. All right. So let's go ahead and get to that. So the next step that we need to get there is to take or to know how to take the Laplace transform of derivatives and differential equations. Okay. All right, so let's look at derivatives first. So we can take the Laplace transform up to the second derivative, which is all that we need. Okay. So the Laplace transform of, let's say, df dt. Okay, so the first order derivative is equal to s times big F of s minus little f of 0. Okay. All right, so a couple of things to note here. So on the one hand, you can see that, when you take the Laplace transform of a derivative of a function, right? One thing that comes out is that you're going to multiply by s. Okay. Okay. So you're going to take, so basically the Laplace transform of a derivative is the Laplace transform of the original function f, right? And the way that you get its derivative, and you just multiply it by s, okay? And that's kind of a direct result of the integral transform, okay? The other thing that's interesting here is this guy, right? So, that's not a typo there. So, that second term there is little f, right? And in fact, it's little f of t is equal to 0, okay? So this is a very special quantity here that refers to the initial condition for f. So what you plug in there is actually is going to be a value, right? And so, whenever you are taking the Laplace transform derivatives, 99% of the time it's going to be within the context of a differential equation. And so within a differential equation, you're going to have some initial conditions that you can plug straight in, okay? So that value there, that f of 0, is actually going to be a number that you plug in directly from the problem that's given to you. Okay. All right. So remember I said last time that, when you solve problems with Laplace transform, we kind of eliminate the notion of a general solution. Because if you're going to be solving a differential equation with Laplace, you need to have the initial conditions. Otherwise, it's impossible to even take the Laplace transform. Okay. Okay, so then let's also look at the expression for the second order derivative. Okay, so Laplace transform of d squared f dt squared. Okay, this is equal to s squared times big F of s. Okay, so you can see we have our multiply by s trick again, right? So our second derivative, we're going to multiply by s squared instead of just s. Okay. And we have two terms here regarding the initial conditions. We have minus s times little f of 0. So that's one initial condition term minus df dt little f at t is equal to 0. So actually, let me box these two just because they are going to be. Okay. All right, so now that we know how to take the Laplace transform of derivatives, we can then apply this directly to our differential equations. Okay. Before I do that, any questions on these here? Okay. All right, so let's go ahead and apply this to a differential equation. Okay. So to solve an ODE using Laplace, so there's a 3-step process to follow when you're solving an ODE with Laplace. Okay. So step one is to take the Laplace transform of the entire differential equation. And so that includes all of the derivative terms, okay, which you know how to do now because, the expressions are written right above there, okay? Now, when you take this Laplace transform, you're going to leave the Laplace transform of the solution as an unknown, okay? Okay, so by doing step one, this is going to reveal an algebraic expression. Okay. An algebraic expression for the unknown solution in the Laplace domain. Okay. But the important thing is that it's all algebra. Okay, so step two, okay, now that you do have that algebraic expression, right, you can then use algebra to solve for that unknown solution. Okay. which usually it's pretty straightforward to do. So it's basically just a little bit of, moving some terms around. You maybe factor out some terms of S, and then you just divide. So step 2 is usually pretty fast. Okay. All right, and then once you're done with that, step 3, okay. So once you do step 2, you have kind of an explicit expression for your solution in the Laplace domain, okay? So technically that's the solution, but Laplace domain is usually not helpful for the most part. And so step 3, we need to take our result from step 2 and take its inverse in order to get the solution in the physical domain. Okay. All right, and so that's it basically, right? And so it's all just kind of algebra. So you don't have to go through, characteristic equation. You don't have to go through applying the initial conditions. There's no undetermined coefficients. It's a very straightforward process. Except I did leave a very important step here, which is the part that everyone hates about Laplace, right? So this usually occurs between step 2 and step 3. So this is kind of like a step 2A, I guess you can say. And it's a little step that, again, I think you probably learned this a long time ago and just thought that it was just a weird math party trick. But it's, I'm almost even ashamed to say it, but it's partial fraction decomposition. Because I'm ashamed of it. All right, so the partial fractions is kind of what people associate with Laplace. And so, usually first lecture in Laplace, everyone's like, yeah, this is great. This is a lot of fun. We use the table, everything. Algebra was great. And then we get to the partial fractions. And everyone's like, this sucks. I don't want to do this ever again. But we got to do it. That's the part of it. Okay. So let me kind of show you kind of why we need the partial fractions to begin. Okay. So let me kind of skip ahead. So let me kind of show you an example. Okay. So I think this will be kind of a good preview of kind of where we're going, but you'll see we're eventually going to get stuck because we're going to reach a point where we can't proceed without the partial fractions. Okay. Okay. All right. So let's do this example. We won't be able to solve it just yet, but we are going to come back to it. Okay. Okay. So let's say we have the equation d squared y dt squared minus y is equal to t. Okay. And we need initial conditions. So it's going to be subject to y of 0 is equal to 1, and then dy dt at t is equal to 0 is equal to 1 as well. Okay. Okay, so let's go ahead and follow the process here as we kind of outlined up above. So let's do step 1. Okay. So let's take the Laplace transform of every term here. Okay. And remember, Laplace transform is a linear operator, so we can just take the Laplace transform of each of these terms individually. Okay. So we're going to take the Laplace transform of the second derivative of y minus the Laplace transform of y is equal to Laplace transform of t. Okay. All right. Now, of course, we don't know what y is. And so when we take its Laplace transform, we're just going to leave it as a generic expression for y. Okay. Okay. All right. So we take the Laplace transform of d squared y dt squared. That is the second derivative. And so from that, we end up with s squared big Y of s. Okay. We don't know what y of s is, but that's our unknown in the equation. Okay. Minus s times little y of 0 minus dy dt at t is equal to 0. Okay. All right, next we have the Laplace transform of just y by itself. And so that is just y of s. Okay. Again, unknown. That's what we're going to be solving for. Okay. And then we have the Laplace transform of t. And so we go back to our table. We say the Laplace transform of t is 1 over s squared. Okay. So next step, let's go ahead and plug in our initial conditions. So let's go ahead and plug in for y of 0 and dy dt at 0. Okay. And so this gives us s squared, big Y of s, minus. So at y of 0 is 1. So that's going to be a minus s, minus another 1, which is dy dt at 0. All right. Okay. So then now that we've plugged everything in, we've taken the Laplace, step 2. Okay. Step 2 is that we need to solve for big Y of s. Okay, so we need to solve our algebraic expression for our unknown solution in the Laplace domain. Okay. Okay, so first thing I'm going to do is I have an s minus 1. I'm going to go ahead and move that to the other side of the equation. Okay. All right, and so we have s squared times y of s minus y of s is equal to s plus 1 over s squared. Okay. I'm going to factor out y of s from the left-hand side. And so that gives us y of s times s squared minus 1 is equal to s plus 1 over s squared. Okay. So last thing to do to solve for y of s, we just need to divide both sides by s squared minus 1. And so we get y of s is equal to, I'm going to separate into the two terms. We have an s plus 1 divided by s squared minus 1 plus 1 over s squared times s squared minus 1. Okay. Okay. One other thing you can do, you may have noticed this already. And so the reason I kind of separated those out is that if you have s squared minus 1, that is in the form of, a squared minus b squared. So this s squared minus 1 is essentially s plus 1 multiplied by s minus 1, right? It's kind of the classical form. And so if we do that, that s squared plus 1 on the numerator and denominator kind of cancel out. Okay. So we have y of s is equal to 1 over s minus 1 plus 1 over, s squared times s plus 1 times s minus 1. Okay. Okay. So that first term there, we can invert this one already, right? Because that's step 3. So step 3 is to basically invert y of s to get y of t, okay? Right, because we always want our solution in the physical domain, or I guess the time domain, right? So that first one, 1 over s minus 1, that's just basically our first shifting theorem, right? So we have a 1 over s minus 1. So this is basically e to the t, right? So that's easy, okay? Second term, right? So second term, we can look at our table and we can try to see if we can find a matching entry for this. You can search all you want, but there is no such entry like that in the table or anything that even comes close, right? So essentially we have s to the power 4 in the denominator, right? Because we have s squared times s plus 1 times s minus 1. Right? So that we have nothing in our table that has s to the 4th power, okay? But we still need to invert this. And so the only way to move forward here is to take that kind of monstrous expression at the end there and then apply partial fraction decomposition to decompose this into separate fractions added together that we can, invert. Okay. All right. So now we kind of get into the meat and potatoes of Laplace transform, doing these partial fractions. Okay, but before we kind of jump into that, are there any questions in terms of what we've gone over so far? Okay. All right. So what is the idea of partial fractions? So this is kind of like a, kind of like a side quest, but a necessary side quest in order for us to continue, right? So let's do partial fraction decomposition. Okay, so the whole idea with partial fraction decomposition is to basically take an expression, a complicated fraction expression, and decompose it into separate terms that we can add together, where the denominators are simple. Okay. Okay. So we're literally taking the denominator and decomposing it into separate terms to make it easier. Okay. And again, the whole idea is to, by performing partial fractions, our result at the end will be an expression that we can more easily apply our, inverse Laplace table to. Okay. Now, the one we just did in the example, this one's a little bit complicated, so I'll kind of save that one for later, but I'll do kind of a simpler one here just to kind of illustrate the process. Okay. Okay, so let's look at the following example as kind of an illustration of how to perform this partial fraction. So, again, the hope is that you've kind of seen this before. Maybe you saw it many years ago, and so this is kind of hopefully just kind of jogging your memory. Okay, but I will try to be as explicit as I can about every step, just so that you can kind of recreate it. Okay, so let's say we have f of s is equal to 3s plus 2 divided by s squared plus s. Okay. And just like our previous problem, let's say that this is an expression that we obtain by solving a differential equation. And so the goal for this is to find its inverse. Okay. All right, so just like our previous expression here, we don't have an entry in our table that has s squared plus s on the bottom. Okay. Now you might be thinking, if you think back to our first example we did today, right? What if we try to complete the square, right? So if we try to complete the square in the denominator here, right? And so we would have to add, a 1/4 to this, but then we'd have to subtract a 1/4 as well. So that, we kind of end up in the same issue because we don't have an entry in our table which has a minus constant. Okay. So the only way forward is to decompose this. So first thing I'm going to do is I'm going to take my denominator here and then just try to factor out as much as I can to kind of get as many separate terms as possible. Okay. Okay. And so we have 3s plus 2 in our numerator. And I can see in the denominator there, I have a common factor of s. And so I'm going to factor that out. So you have s multiplied by s plus 1. Right. Okay. Now, this doesn't help us right away, right? Because we still don't have an expression that we can directly inverse. But it does tell us, which components are making up our denominator, okay? So we can see here that, we have basically two functions that are multiplied by each other in the denominator. We have a function which is just s and a function which is s plus 1, okay? So the way partial fractions works is that, since we have these two components in the denominator, we can break them up into separate fractions, but just add them together. Okay. All right, and so we're going to have one fraction that is just over s, and then to that, we're going to add another fraction that is over s plus 1. Okay. All right, so that right there on the right, this is our fractional decomposition, right? So we kind of broken up our fraction into these two terms. Okay. Now, when you decompose this, right, we can't just magically create these fractions. We have to make sure that our decomposition is still equivalent to our original fraction that we had, okay? And in order to do that, we need to solve for what should be in the numerators of these two fractions, okay? So we've already determined what's going to be in our denominator, but we don't know what's going to be in our numerators, okay? So we're going to set just generic coefficients there, generic numbers, a and b, right? And the idea with the decomposition is to solve for the values for a and b such that our decomposition is equivalent to our original function. Okay. Okay. So that's kind of the whole idea with partial fractions is you set up your decomposition and you solve for the values of the numerator such that it's equivalent. Okay. And hopefully what you've seen from our Laplace is that, what happens in our numerator, is not nearly as important by what happens in our denominator. Because, usually what happens in the numerator, we can kind of, factor out constants and such in order to make things equivalent to our table. The denominator is kind of the part that's a bit more harder to work with. Okay. Okay. So let me go ahead and write this down here just so that we have a bit more room. So we have 3s plus 2 divided by s times s plus 1 is equal to a over s plus b over s plus 1. Okay. All right. And then our goal at this point is to solve for the values for a and b in order to make this, these equivalent. Okay. So how are we going to do that? So the way that we solve for the values is that we're going to multiply by the entire denominator on both sides of the equation. So we're essentially going to multiply both sides of the equation by s times s plus 1. Okay. So that essentially is going to eliminate all of the denominator terms on both sides of the equation. Okay. And then the idea is to get something left here that we can solve for a and b. Okay. So doing that, right? And so that's going to eliminate all of the denominator on the left-hand side. So left-hand side, we just have 3s plus 2. Okay. And on the right-hand side, we're only going to have partial cancellation just because each of the a and b terms, they don't have the full denominator, okay? So for the a term, we're going to have a. So the s in the denominator there is going to cancel out with the s there. So we're going to have a times s plus 1, okay, plus b. So for the b term, the s plus 1 is going to cancel out, but not the s. And so we're going to have plus b times s. Okay. All right. All right, so let's go ahead and combine like terms on the right-hand side. So we're going to combine like terms according to the powers of s. Okay. Okay. And so you should notice that this process that we're going through is actually very similar to the process we go through for undetermined coefficients, right? Partial fractions is essentially the same thing. We have undetermined coefficients a and b. It's just that, the purpose and how we get here is a bit different. Okay. All right, so let's go ahead and combine the like terms. So we have 3s plus 2 on the left. On the right-hand side, we have s times a plus b plus a. Okay. All right. So now what we can do is that we can form a linear system of equations to solve for a and b based on the powers of s. Okay, so on the one hand, if we look at all the terms multiplied by s, we have 3 on the left and then a plus b on the right. And so that tells us 3 must equal to a plus b in order for the two sides of that expression to be equal. Okay. And then on the other hand, we have a 2 on the left-hand side, and there's only one constant term on the right. So that means 2 has to equal to a. All right. So this system of equations is very straightforward to solve. So right away from the second equation, we can see that the value of a is equal to 2. And if the value of a is equal to 2, we plug that back into our first equation. We get 3 is equal to 2 plus b. It's the only value of b that makes that possible is if b is equal to 1. Okay. Okay. So now that we have the values of a and b, we can go ahead and plug that back into our partial fraction. So that means we have 3s plus 2 over s times s plus 1. This is equal to 2 over s plus 1 over s plus 1. And that is our partial fraction decomposition. Any questions on how we got that result for the partial fraction? Okay. All right, so now that we have our expression in this form, we can go ahead and take its inverse because 2 over s and 1 over s plus 1, these are both expressions that are in our table. Okay, so the inverse Laplace of 2 over s, the Laplace transform of just 1 was 1 over s, remember? And so the inverse Laplace of this is going to be 2. Okay. And then the inverse Laplace of this is e to the minus t. That's just our first shifting theorem. Okay. That means f of t from this Laplace expression is 2 plus e to the minus t. All right. So most of the time, when you're using Laplace transform to solve differential equations, you're going to need to do partial fractions in order to get something that you can actually invert. Okay. Now you don't have to do partial fractions, and so if you end up with an expression that you can invert without partial fractions, then by all means do it. But most of the time you're going to get expressions where there's not a matching table entry, and so you need to do partial fractions in order to get something that you can invert more easily. Okay. All right. So let's do one more example today before we head out for the week. Okay. So this one will be a new interesting case. This will be a bit more consistent with what we went over for the example, earlier. All right. So let's say f of s is equal to s squared plus 1 in the numerator. And then in the denominator, we have s times s minus 1 quantity cubed. Okay. All right, so just like the previous problem, we want to find the inverse Laplace of this expression. Okay. All right, so just like before, or just like our previous example, we don't have an expression here that we can immediately invert. Okay, so we do need to do partial fractions, but the complicated thing here is that this s minus 1 in the denominator appears 3 times. That's why it has a cube. All right, and so what that means is that, when you take your partial fraction decomposition, not only do you need to have a term for s minus 1 quantity cubed, you need to have a partial fraction term for all lower powers as well. Okay. Right, so we have s squared plus 1 over s minus 1 quantity cubed. Okay. Okay. So our partial fraction decomposition for this, we're going to have one term for just s. We have a over s, right? So that is that's the first term in our denominator. Okay. But since we have s minus 1 quantity cubed, we need to have 3 terms that account for this. Okay. So we need to have a b divided by s minus 1. Okay, so that's the first power plus c over s minus 1 quantity squared plus d over s minus 1 quantity cubed. Okay. So whenever you have a term that appears multiple times in the denominator, you need to have all of the terms that lead up to it in your decomposition. Okay. Okay, now of course, this does multiply our work quite a bit. So we have 4 constants to solve for. Okay. But the process is going to be just like the previous one. Okay. So first thing we're going to do is we're going to multiply this entire equation, both sides, by the complete denominator. So we're going to multiply by s times s minus 1 quantity cubed. Okay. So let's go ahead and do that. We're going to multiply this by s times s minus 1 quantity cubed. Okay. So obviously that's going to cancel out everything in the denominators. Okay. So on the left-hand side, we're just left with s squared plus 1. And then right-hand side, this is where things get a little dicey, a little interesting. Okay. All right, so first we have a over s, and so the s is just going to cancel out with the s there. So you have a times s minus 1 quantity cubed. Okay, then we have our B term, so that's gonna be B times S, right? So the S minus one is only gonna cancel out one power, so we're gonna have S times S minus one quantity squared. Then next we have our C term, so that's C times S minus one. Okay. And then we have a plus D times S. That is the last term in our decomposition. Okay. Okay. All right, so we got a lot of foiling to do. We even have a cubic foil that we need to do. Okay. Okay, so next step, there's no pretty way to do this, and so the only thing is just to kind of, foil everything out, multiply everything out, distribute it, because eventually we need to combine like terms of powers less. Okay. We have S squared plus 1 is equal to A times S minus 1 cubed. Okay. Right. And so I don't expect you to have, S plus A quantity cube in your back pocket, although that is one of the perfect, terms in the pyramid. But if you cube this out, you end up with S cubed minus 3S squared plus 3S minus 1. Okay. All right, next we have B times S minus 1 squared. So that's B. Okay. S minus 1 squared, that's S squared minus 2S plus 1. We just multiply an S by that. We get S cubed minus 2S squared plus S. Plus C. So C gets a little bit simpler here. So C, this is multiplied by S squared minus S. Okay. And then D is the good child. There's no foiling to do. So D is just multiplied by S. Okay. All right. All right, next thing to do, we are going to go ahead and combine the like terms by the powers of S. Okay. All right, so we have S squared plus 1 on the left-hand side. Right-hand side, we're going to look at all the S cubed terms. So S cubed here, we have, what do we have? So we have an A plus a B. I think that should be it. Okay. All right, next we have, let's see. Next we have the S squared terms. So S squared. All right, so S squared, what do we have here? We have a minus 3A. My pen is dying on me. We have a minus 2B. Okay. And a plus C. Okay. So that's everything with an S squared. All right, next we have everything with an S. And so we have a 3A that comes from the first term. We have a plus B that comes from the second term. And a minus C that comes from the third term. Oh, and a plus D. All right, and then finally we have just a constant term. So our only constant term here comes from the A, and so that is a minus 1 times A. All right. So yeah, take these steps pretty slowly, and just because it's very easy to kind of make a mistake, especially when you are trying to cancel out terms and move them down. So you don't want to miss a term. You don't want to kind of miss add a term as well. Okay. All right, so now we can go ahead and set up our system of equations. So we have 4 equations here for 4 unknowns. Okay, so we need an equation for s cubed. We need an equation for s squared, for s, and our constant term. Okay. Okay. So for s cubed, there's no s cubed on the left-hand side, so we're gonna have equal to 0. So you have 0 is equal to a plus b. Okay. For our s squared term, we do have an s squared on the left-hand side, so that coefficient is just 1. That's going to be equal to minus 3a minus 2b plus c. Okay. There is no s term on the left-hand side, so that's going to be equal to 0. And the right-hand side, we have 3a plus b minus c plus d. Okay. And then for this negative. And then for our constant term, we have 1 is equal to minus a. Okay, because on the left-hand side, we do have a 1, and on the right-hand side, we have minus 1 times a. Okay. Okay. So quite the significant system here. And so normally for equation 4 unknowns, this is not a trivial exercise. But luckily for this problem here, we can kind of solve things in sequence. And so even though it's 4 equations, you can hopefully kind of see the order here. Because first thing we're gonna look at the last equation, right? So from the last equation, we get that the value of a has equal to minus 1. Okay. We then plug that into our first equation up here, because our first equation only applies for a, only involves a and b. Okay. And so based on the fact that a is equal to minus 1, this tells us that b must equal to 1 in order to satisfy that equation. Okay. All right, we then plug that into our next equation here. So we have 1 is equal to minus 3 times a, so that is a positive 3, minus 2 times b, so that's a minus 2, plus c. Okay. Right, so we're in luck here because we work out this arithmetic, and the only way for this to happen is if c is equal to 0. Okay. So zeros are great because it means that one of our partial fraction terms is just going to go to 0. Okay. And then finally, we plug everything back into the last equation here, so that we have a 0 times is equal to 3 times a, which is minus 3, plus b, which is 1, minus c, which is 0, plus d. And then from this, we get d is equal to 2. All right. So let me go ahead and circle all the values of our coefficients here. Okay, so let's go ahead and plug all these back into our decomposition. Okay. And so from our decomposition, we get s squared plus 1 divided by s times s minus 1 quantity cubed. This is equal to, first we have a, which is minus 1, so that gives us a minus 1 over s. Okay. Then we have b is equal to 1, that gives us a plus 1 over s minus 1. Okay. C is 0, so we're not going to worry about it. And then d is 0, so that's 2 divided by s minus 1 quantity cubed. Okay. No, so that s minus 1 quantity cubed, that is the Laplace transform of t squared with a shift. Yeah. Yeah, so everything here is ready to be inverted because we have a minus 1 over s right? So this right here is the Laplace transform of -1. Okay. This right here, this 1 over s minus 1, this is the Laplace transform of e to the t. Okay. And then this last one, right? We have 2 over s minus 1 quantity cubed. So we know that the Laplace transform of t squared is 2 over s cubed. Okay. Okay. And so that means that the Laplace, so the inverse Laplace of 2 over s minus 1 quantity cubed, that's just t squared with a shift. Okay. So this is the Laplace transform of e to the t times t squared. Okay. All right, and so we're out of time, and so I didn't write this as an FT, but there's all the inverse transforms. Okay, so once you do the partial fractions, you should get expressions that are easily inverted, and you may have to apply a shift just to kind of get it there, but yeah, that's partial fractions and Laplace in a nutshell. Any final questions on this example before we wrap it up for the week? Okay, all right, so that's all the time we have for today. So when we come back on Tuesday, we will start to apply these to solve for differential equations. So I have a couple of examples with that. And then we'll move on to step and impulse functions. All right, so thank you everyone for coming today. I hope you guys have a good rest of your week. And I will see you guys next week on Tuesday. Thanks, Pablo. Thanks, Lorenzo. See you, Anthony.